let us first take up the topic main memory and try to study in depth this thing in depth, and also try to see and also see what is the architecture and organization of a main memory. So when it comes to main memory, the main technology that is used is semiconductor integrated circuits. So the main memory is basically, it is fundamentally made up of semiconductor integrated circuits. So it is something which is related to semiconductors. And we know it very well that there are two main types of main memory. One is the RAM, another is the ROM. RAM means random access memory. ROM means read-only memory. Technically speaking, both RAM as well as ROM are random access. Both are random access memories, which means that a CPU can randomly access any memory location within RAM and ROM. So if a CPU wants to access the location number 50 in RAM, it can directly access that 50 location. It doesn't have to go serially. It doesn't have to go to 1, then 2, then 3, 4, 5, 6, 7, then to 50. No, it doesn't need a sequential access. The mechanism, the architecture is such that a CPU can directly access any memory location of RAM as well as ROM. So in this sense, both RAM as well as ROM are random access memories. So that this is the reason that we sometimes call RAM as read-write memory. So a memory in which we can read as well as write. And the other thing, ROM, we call as read-only memory, means a memory in which we can only read. So a CPU can write something, some number, some program, some data into RAM. It can also read that thing from RAM. But when it comes to ROM, the CPU can only read things. It cannot write into ROM. It cannot put data or programs into ROM. Okay, then there are two types of RAM. One is static RAM, another is dynamic RAM. So what is the difference between these two, static RAM and dynamic RAM? A static RAM is one which is made up of flip-flops, and a dynamic RAM is made up of capacitors, and these capacitors are there because of MOSFETs. So most transistors are there in the dynamic RAM, which provide capacitors there, and in the static RAM we have flip-flops. What difference will there be because of this difference in the design of these two? There, this creates multiple differences between these two types of RAM. Since static RAM is made up of flip-flops, and to access a flip-flop takes less time than to access a capacitor, because a capacitor needs recharging. So static RAMs are faster than dynamic RAMs. A static RAM is faster, means the access time of a static RAM is less than the access time of a dynamic RAM. This is the reason that cache memory is usually made from static RAMs, and the main memory, the RAM, which usually we call as RAM, is usually made up of dynamic RAM. Okay, why is this dynamic RAM slow? Because we know that the capacitors, they lose charge continuously. So every few milliseconds we need to recharge capacitors. Since we need to recharge capacitors every few milliseconds, so this extra amount of time goes with this recharging. So naturally dynamic RAM becomes slower as compared to static RAM. But since capacitors are cheaper than flip-flops, dynamic RAMs are cheap. Static RAMs are costly. So that's why when we put a 4 GB or a 2 GB RAM into a computer, into a laptop, into a PC, we use dynamic RAM because it is cheap. It has a disadvantage, but it is cheap. Static RAMs have flip-flops, and we know flip-flops can store bits. So the job of a RAM is to store bits. That is what flip-flops will do. So flip-flops will store bits, zeros and ones. So that is the purpose of memory, storing things. And a dynamic RAM has capacitors, and the bits, ones and zeros, are stored in the capacitors in the form of charge. The charge will depict whether the condition is a 0 or a 1. Okay, one more thing, that RAM is a volatile memory. It is a temporary memory in the sense that if we put off the power, then the contents of a RAM become invalid. Whatever is RAM in RAM, that becomes invalid when we switch off the power. But the second type of main memory, the ROM, it is a permanent storage. Even if we switch off the power, the ROM will not lose its contents. What is the purpose of using ROM? The purpose of using ROM mainly is to store the program that will start a computer. This is the reason that the manufacturer puts a small chip inside a PC, inside a computer, which we call as a ROM, which has a very small size. And what is stored on that ROM? It stores usually a program called Bootstrap loader. What is stored on ROM? It stores a program called Bootstrap loader. What is Bootstrap loader? Bootstrap loader is a program which starts a computer. So when we put on the power button of a computer, the hardware is organized in such a way that the first instruction of the Bootstrap loader is executed. And after this whole program of Bootstrap loader gets executed, what happens? The operating system is transferred to RAM. So The point is that whenever a computer is put on, there is a program in ROM called Bootstrap loader. The job of this program is to bring OS, the operating system, from hard disk to RAM. It brings, it doesn't bring all of operating system. It brings the um, essential parts of an operating system from the hard disk into RAM. So this is the major job performed by a ROM. This thing, storing the program which transfers, which makes this transfer. The essential part of an operating system is transferred to a RAM. And once the operating system comes to RAM, then the job of ROM is this over, and the control is given to the RAM, to the operating system. Now all other things will be managed by the OS, the operating system. So the ROM acts as a starter in a computer. There are some other things also stored in ROM. For example, some tables of constants are there. Those constants which do not change. So the manufacturer may put some table of constants also in ROM. But the basic job of ROM is to start a computer. Let us have a look at a typical RAM chip. So this is a block diagram of a RAM chip. So here, in this example, the size of the RAM chip is 128 into 8. So what does this mean? That this box represents a RAM chip, random access memory chip, with a size of 128 into 8. This means that you can, in simple terms, remember that this means this box has 128 rows and 8 columns. So this means that this box has 128 rows and 8 columns. In each column, there are 8 flip-flops. And if it is made of capacitors, there will be 8 those blocks. So let us say this RAM chip is made up of flip-flops. So there will be 128 rows in this RAM chip, and in each row there will be 8 flip-flops. So that means 8 flip-flop in the first row, 8 in the second, 8 in the third, and so on up to 128 rows. So that means how many bits can this RAM store? This RAM can store 128 into 8 bits in total. This 8 we usually call as a word, because this is the size of one row, this 8. So we usually call this one row as 8, as word. So we say the word length here is 8, which means that at a time 8 bits can be transferred to and fro from the RAM. So that is why the diagram is showing that the data bus, the bus which transmits data from the RAM to CPU and CPU to RAM, is 8 bits. So the bus, the transmission medium between CPU and RAM, the bus is 8 bit. Why is it 8 bit? Because the RAM has a word length of 8 bits. Okay, why is it bidirectional? Why is it showing two arrows, this way and this way? Because in RAM the CPU can write and from RAM the CPU can also read. So it is a bidirectional bus. How many bits the CPU can read or write at a time? It can read or write 8 bits. Why? Because the size is this 8. So this 8 depicts that a CPU can at a time read 8 or write 8 bits into the RAM, which is same as one row of a RAM. Okay. This 128 means there are 128 rows here, and we see some other things from left side here in the RAM. So we can see that a RAM will have a read line, it will also have a write line. So what does that mean? These are control lines. So the CPU will tell whether it wants to read or it wants to write from RAM. So if the CPU wants to read something from RAM, it will put this read line to 1. And if it wants to write something into RAM, it may put this write line to 1. And in some chips, there may be only one line for read and write. If it is 1, it may be read, and if it is 0, it may be write. That is also possible. Okay, now what is this thing, this 7-bit address, AD7, address 7? Since this RAM chip has 128 rows, which means there are 128 memory locations in RAM. So if we name these memory locations, the first will be 0, then second will be 1, then 2, 3, 4, 5. It will go up to 127. So if we name the rows in the RAM, there will be 0, 1, 2, 3, 4 up to 127. So there are in total 128 addresses in the RAM. Okay, how many bits do we need to address 128 lines? This we have to see, we have to calculate this. How many bits? So in binary we study that if we have to name two things, we need 1 bit. We may call one thing we may call 1, and the another thing we can call 0. If we have 4 things, we need 2 bits to name them. So the name of first thing will be 00, the name of second thing will be 01, the name of third thing will be 10, and the name of fourth thing will be 11. If we have 8 things, we will need 3 bits. If we have 16 things, we need 4 bits. If we have 32 things, we need 5 bits. If we have 64 things, we need 6 bits. If we have 128 things, we need 7 bits. Fine. So it can directly be calculated by a formula of log, that for 128 memory locations, how many bits are needed? Log to the base 2 128, which is the same as 7. So that is why we need 7 address bits to address 128 locations. We need 7 address bits. Had it been 32 here in place of 128, we would have needed 5 bits. Had it been 4 here, we would have needed 2 bits. So the address bits means how many bits we need to address this thing, this block. Since this block has 128 memory locations, this means that we need 7 bits to address this thing, this block. And lastly, what is this chip select 1 and chip select 2? So CPU has to select this box. it is possible that in a computer there will be many RAM chips and also ROM chip or many ROM chips. So how to select those things? For that, CPU will use this thing, chip select 1 and chip select 2. In some chips, it may be only one chip select, it may be two or even more chip selects. The purpose of using chip select is that to select that block, that RAM chip. If there are many RAM chips, CPU has to select any one. So that to select that one RAM chip, he uses this chip select. Okay, we can draw a function table for this RAM, 128 into 8 RAM. So this is a very simple table. So since there are these 4 lines here for selection of the chip and reading writing, we write these 4 here. So this is chip select 1, chip select 2. A bar implies that to select this chip, this line must be 0. So whenever you find a bar somewhere like this, it means that the input from here should be 0. If it is 0, bar will convert it into 1, then only this chip will be selected, otherwise it will not be selected. In other words, that since this does not have a bar, this should be 1, this should be 0. When the CPU says, here it says 1, here it says 0, then only this chip will be selected, otherwise this chip will not be accessed. So the thing is that this should be 1 and this should be 0. So that is why here we are showing that this should be 1, this should be 0, then only something will happen, 1 0 1 0. At all other combinations, whether it be 0 0, be it 0 1 or it be 1 1, in all these combinations the data bus will go into high impedance state. What is a high impedance state? A high impedance state is a state when there is no transmission of data. There is, we can say, there is nothing on the data bus. You must be knowing that in digital, in binary, there are two states. Either it will be a 0 or a 1. It will be a high state or a low state. But there are certain mechanisms to create a bus. There is something called a tri-state buffer, through which we create a bus, a data bus, which has 3 states. So this is an exception to the general rule that there are only 2 states. So some data buses, the data buses can be created using 3 state buffers, and by that there will be 3 states. One state will be high, that is 1. The second state will be 0, low, and there will be a third state called high impedance state. High impedance state means that the bus is not carrying anything. So in this third state, high impedance state, the bus is not carrying anything. So obviously what should happen whenever this is 0 0 0 1 or 1 1, this chip will not be selected, and if the chip is not selected, data bus should not carry anything. So that is why we write here high impedance, means the data bus in these conditions does not carry anything. Now the fourth condition, where this will be 1 and this will be 0, this is 1 and this is 0, means this chip will be selected. And let us see what happens in that condition. If this is 1, this is 0, the chip will be selected. Now after selecting, what do we have to do? Whether we have to read, whether we have to write, it is the CPU which will tell us. So let us see, the CPU here is saying 0 0, means neither read nor write. So in such case, again there will be high impedance state. Yeah? Meaning the function will be nothing. There will be nothing done. No transmission, neither read nor write, and the bus will be in high impedance state. In other words, the bus will not carry anything because the CPU is neither reading nor writing. For the same combination, if the CPU says 0 1 means no read but write. So obviously what will happen? Writing will happen. So what is the write operation? Write means bring the data from CPU to RAM. This is called write. And if the read is on, irrespective of what is on the write, there will be a read operation. So if a read is on, there will be a read operation. And read, what do we mean by read? Read means that the data from RAM is moved to the CPU. So this is the read operation. So this function table represents the working of this RAM. Let us now have a look at a ROM chip. A ROM chip is very similar to a RAM chip. So if I say, for example, that I have a ROM chip which of size 512 into 8, what does that mean? It simply means that this 8 means the size of data bus will be 8. In other words, the width of this, the number of flip-flops in each row is 8. The size of data bus will be 8. And what does this 512 mean? So 512 means that there are 512 entries in this ROM, 512 rows in this RAM, in this ROM. So how many address buses will be there? We can directly calculate that for 512 entries, we need 9 address buses, or we can use the formula that log to the base 2 512, which will be 9 address buses. So to address 512 things, we need 9 address lines. Okay. In this ROM chip, we don't need this read and write line, because this is very logical. Whenever a ROM chip is selected by the CPU, it naturally means that it has to read, because there will be no write operation in a normal ROM. In a traditional ROM, there is no write operation. So whenever a ROM chip is selected, it naturally means that the CPU wants to read. So there will be no separate read and write lines here. Otherwise, the structure is same as that of RAM. Now, there is another thing that we call as memory address map. What is that? Memory address map, it is a pictorial representation of assigned address space for each chip in a system. Meaning that in a pictorial form or in a tabular form, we write what is the address space of each chip. So if there are many chips in a computer, we just summarize things. What is the address space? How much address, how many addresses, and from which range to which range each chip will have. If we write this in a tabular form, in a pictorial form, that is called memory address map. So mapping of addresses, that is why it is called a memory address map. Let us take an example. Let us say I have a computer, a microcomputer, which has 4 128 into 8 RAM chips, 1, 2, 3, and 4, and it has one ROM chip of the size of 512 into 8. So this is, we are taking an example where we have 4 RAM chips and 1 ROM chip, and this is the size. And if we look at the total size of the RAM, this will be 128 plus 128 plus 128 plus 128, which means 512. So the total size of RAM will be 512 into 8, and the total size of ROM is 512 into 8. And in this example, what is the total size of memory? The total size of memory, we will add up all. This will come up to be 1024 into 8. So the total size of memory, which includes 4 RAM chips and 1 ROM chip, if we add them up, it becomes 1024 into 8. So the total size of memory is this much. So let us denote the addressing of each chip in a table. So we have 5 things. So here we have 5 components. Component RAM1, RAM2, RAM3, RAM4, and 1 ROM. Let us go to RAM1. The RAM1 is 128 into 8 size. 128 implies that there will be 7 address buses. So 7 address buses. So 1, 2, 3, 4, 5, 6, 7. So the first 7 bits of the CPU address will be the address bus of first RAM. So address can be anything. We don't know what it is. At any instant of time, the address will be anything which will be decided by the CPU. For that purpose, we just keep X's here. So this is 7. So 7 X's here. So this implies that this is the address of the first RAM. For the second RAM again is of the 7-bit address. So again 7 X's. Third RAM the same thing. Fourth RAM the same thing. 7 X's because it is 7 bits address. And then we have the ROM. The ROM in this example is 512 into 8, means 512 implies there will be 9 address buses. So the 9 address buses means 1, 2, 3, 4, 5, 6, 7, 8, and 9 cross. So the address of ROM will be 9 crosses. Okay, good. Now, since there are many RAM chips and also a ROM chip, how will the computer distinguish between the various RAM chips? If the CPU says, for example, the CPU gives some address. It says I have to access the address number 99. Now a confusion arises. The 99 address of which RAM? Whether the 99th address of this RAM or this RAM or this RAM or this RAM. To remove this confusion, we need extra bits, right? Since we are there will be confusion. 99, I have to read 99 memory location, 99th memory location, but 99th memory location of which RAM? The first RAM or the second RAM or the third RAM or the fourth RAM? To remove this confusion, there is a simple way. Just use 2 bits. So if I have to access this RAM, I will call it 00. So this RAM I will call at 01, this RAM I will call 10, and this RAM I will call 11. So very simple. If I have 4 things and I have to name them, let me call this 00, 01, 10, 11. That is what is here. So the 8th and 9th bit, what is this? For the first RAM it is 00, for the second it is 01, for the third it is 10, and for the fourth RAM it is 11. So the confusion will be solved. Which RAM we want to access? Fine. Now the last thing, which is again another problem, another thing. that if the computer says, okay, I want to access memory location 99, but there will be another question, who's 99? 99 of RAM or 99 of ROM? Because there are two categories of memory, whether you want to access RAM or you want to access ROM. So this is one category RAM, this is another category ROM. Again, simply this problem can be solved by one bit. If the CPU says 0, it means RAM. If the CPU says 1, it means ROM. So that is why we are using a 10th bit. If the CPU says 0, 0 will naturally imply RAM. And if the CPU says 1, automatically it will mean this will mean ROM. So in this way, by using 10 bits, we can solve this problem, and any memory location from anywhere can be selected. We can also cross check this thing, because the total size of this whole memory is 1024 into 8. 1024 implies 10 address lines. So we can cross check that there will be 10 address lines in total for whole this system. So now we have calculated this address line thing for all this RAMs and ROM. Now if we want to simplify it and we want to see the range, we can convert all this into hexadecimal and also mention the range there. So this thing we have to convert into hexadecimal to make this. One thing is to be noted here, that in this example, this we are supposing that there are 16 bits of total address. So the total address is in 16 bits. So when we convert 16 bits into hexadecimal, it will become 4 digits. So that is why it is 4 digits here, 4 digits here. So total it is 16 bits. But for this thing we are only using 10 bits. The remaining 6 bits will be 0. So they will always be 0. 6 zeros followed by this thing. So let us convert this into hexadecimal. So if I have 6 zeros, then I have this thing 0 0 0, and the first address will be all zeros. And if I convert this 16 zeros into hexadecimal, it becomes 0 0 0 0. Okay, what will be the last address? 6 zeros followed by this 3 zeros, and the last address will be all ones. So put this all as ones, 7 ones. So if I convert this 16 digit number into hexadecimal, it will become, first zeros will be 0, second 4 zeros will again be 0, then 0 1 1 1 means 7, 1 1 1 1 means F in hexadecimal. So the range, the lowest address will be this, the largest address will be this. So the first address in this RAM in hexadecimal will be 0000, and the last address, the address of the last row will be 007F. So let us see for this RAM now. So then starting there are 6 zeros. So put all this to 0, the first address. So if you convert to hexadecimal, it will be 001, and 000 means 8, and 4 zeros means 0. Okay, the last address will be, put all this to 1. So this will be 001111 means F, 1111 means F. So the last address will be this thing. So the first address of the RAM 2 will be 0080, the last will be 00FF. In the same way, you can do it for other entries also. You just have to put all zeros here, calculate this thing, and then put all ones here, calculate this thing. So this way you can calculate all these addresses. So once this table is formed, we what we have done, we have mapped the addresses onto this table. This this table, this representation is called a memory address map.